Hello. Today we're going to talk about vector functions and space curves. And what we have to talk about really is like the algebra of vector functions and space curves. Once we talk about those, then we can go on to the idea of limits and continuity and eventually get to derivatives and integrals. So a vector valued function, here's one right here. It's when you've got an r of t and it's equal to a vector, and each of the components that's inside of the vector is a function. So we've got f of t, g of t, and h of t. These are all functions. So a vector function is a vector that has functions inside each component, okay? We've dealt with vectors and they had numbers in the components, so that's the difference. Now, because there are functions, we will have to talk about things like the domain of a vector function. And the domain is going to be determined with the valid t values, okay? And we'll get to that in just a moment. You're going to hear some vocabulary come up often, and so it's important to know what is being expressed when I use this vocabulary. So in this new notation, r of t is equal to f of t, g of t, h of t, all in a vector notation. The first function, f of t, that is falling into the x component. And so if we were to look at the parts of the vector and write them out in parametric form, we would see that x is the f of t, y is the g of t, and z is the h of t. So this is the parametric form of the vector function. And that's why you'll hear me refer to the first component in a vector as the x component, or the third component of a vector is the z component. They're one and the same. Okay. Domains of vector functions. So what has to happen is that we have to look at the individual functions f, g, and h, and we have to find their unique domains. Then we look at the intersection of those domains. So this little blurb right here is just saying the domain of f intersected with the domain of g, intersected with the domain of h. And that's going to give us the overall domain of the entire function. All right, limits. With limits, very, very similar to what we did in Calc 1, although most of our limits are going to be a little bit nicer than what we dealt with in Calc 1. The difference here is because we have vectors and vectors have components, we can't just take the limit of the overall vector, like this notation right here. The limit as t goes to a of r of t. We actually have to take that limit notation and distribute it to each of the components inside of the vector. And then we deal with those pieces individually. In the end, we will get some vector that is going to be the, hopefully, if there's continuity, we'll get this. F of a, g of a, h of a, and this is kind of provided all limits exist. If any of the components have a limit that does not exist, then the overall limit does not exist. I'm just going to write that little blurb down here. If any of the components of r of t have a limit that does not exist, then the entire limit of r of t does not exist. Okay, so let's get straight into some examples. This first example, we're being asked to find the limit of a vector, and there are three components of the vector, which means we have three limits to look at. So I actually write it out that way. I go ahead and I write the first one. That'll be the limit as t goes to infinity. And I'm going to rewrite the function. Instead of writing it as t times e to the minus t, I'll write it as t over e to the t. The second one will be the limit as t goes to infinity of the t cubed plus t over 2t cubed minus 1. And the third one will be the limit as t goes to infinity of t times sine of 1 over t. All right, we have three limits and they all bring up something different as we try to evaluate them. The first one, we're looking at the limit as t goes to infinity of t over e to the t. Now we can apply L'Hopital's rule, which says that we, because we're getting infinity over infinity, if we were to just plug in our t value of infinity, that is an indeterminate form, which allows us to use L'Hopital's rule. And with L'Hopital's rule, we would write our equal sign and just put an LH over that because that indicates that, yes, you have equality, but the equality is only true because of a particular theorem. So we use the LH over the equal sign, and then we rewrite the limit as t goes to infinity. And L'Hopital's rule says to take the derivative of the top, so the derivative of t is 1, and divide it by the derivative of the bottom. And the derivative of the e to the t is just e to the t. Now if I were to think about plugging in infinity, the bottom of this fraction would blow up to infinity. And 1 over infinity is going to give us 0. Another way I could have looked at this is I could have just thought about the functions t and e to the t. T is linear, e to the t is exponential. An exponential function always grows much, much, much faster than a linear function, which means that the bottom of the fraction is growing much faster, and that means that the overall fraction will approach 0. But of course, you can always use L'Hopital's rule to get there. This next one I want to do differently. So in 2, we're looking at the limit as t goes to infinity of t cubed plus t, all divided by 2t cubed minus 1. Notice that the degree of the top is 3 and the degree of the bottom is 3. So I can think of this in terms of horizontal asymptotes. And the reason for doing that is because it'll speed up our process tremendously. Asymptotes. Okay. We have some rules with the horizontal asymptotes, and the one that we want to use here is that if the degree of the top and the bottom are equal, then in the limit as t goes to infinity, or as our function approaches infinity, sorry, not our function, as our independent variable approaches infinity, the limit is going to be the ratio of the coefficients in front of those leading terms. And so that means that we're going to get this is equal to 1/2. Because there's a 1, it's kind of an invisible 1, but it is a 1 nevertheless in front of t cubed over a 2t cubed. And the t that's in there, the plus t in the numerator, is nothing compared to the t cubed. And the minus 1 in the denominator is nothing compared to the 2t cubed. So we could just say as t gets super, super big, really we're looking at what's happening with t cubed over 2t cubed, and that reduces to 1/2. The last one, the limit as t goes to infinity of t times sine of 1 over t. If I was to plug in infinity, this would give me infinity times, all right, 1 over infinity goes to 0, and sine of 0 is 0. So this gives me infinity times 0, which is not 0 necessarily. This is almost what we call an indeterminate form. It's not quite. It does need to be fixed. The trick is to take one of the two factors in the numerator and rewrite it in the denominator, flipped over. I don't mess with signs when I'm doing this, but I will mess with the t. So that t that's sitting out in front, I'm going to rewrite my function, limit as t goes to infinity. I'm going to rewrite it so that the sign stays in the numerator, and instead of writing t in the numerator, I write 1 over t in the denominator. So I've written an equivalent statement. I didn't change anything, I just made it look a little different. Now, if I was to evaluate this, I would get 0 over 0, which is an indeterminate form, and that allows me to use L'Hopital's rule. So I'm going to write my equals with my LH over it to indicate that I am applying L'Hopital's rule. So I rewrite my limit as t goes to infinity. The derivative of the top, well, the derivative of sine is cosine of the angle, so 1 over t, but we have a chain rule, so we need to multiply by the derivative of the angle. The derivative of 1 over t is negative 1 over t squared. All right, the numerator's done. The denominator, well, we've already dealt with 1 over t. The derivative of it is negative 1 over t squared. All right, never try to evaluate before you clean up the mess that you make. So notice that in taking these derivatives of the top and the bottom, we have a much uglier expression. However, there is a common factor in the numerator and denominator, so those are going to cross out. That means we can go ahead and say, well, this is just equal to the limit as t goes to infinity of cosine of 1 over t. As t goes to infinity, this is going to be cosine of 0, which is 1. And now, if I kind of follow a bit of a lazy thing, I'm going to go upstairs to where the original limit was and say that it's equal to L vector. That's my limit vector, okay? So that down here I can just say, oh, okay, I found my L vector. It has components. Well, the first component gave us 1. The second component gave us 1/2. And the third component gave us 1. And that's our final answer. So that's how you take a limit. You are going to come across functions that maybe bring up some bad feelings from way back when in Calculus 1, but hopefully it's okay. Hopefully we can work through those, right? Now we're in Calculus 3. It's not so bad. All right. Next thing is the domain. So in this question, I'm asking, what is the domain of the vector function below? Well, if I name these f, g, and h, then I need to find the domains of f, g, and h. So the domain of f is the first part, t over e to the t. So f of t is equal to t over e to the t. Now fractions are only undefined if the denominator is ever 0. E to the t is an exponential function, which is never equal to 0. And so f of t being equal to t over e to the t has a domain of all reals. So we write that funny looking r. The domain of g, here we're going to be examining g of t is equal to t cubed plus t all divided by 2t cubed minus 1. All right, now this is another fraction, and it does have a denominator that could be 0 at some time. So 2t cubed minus 1 cannot be 0, which means that t cubed cannot be 1/2, which further means that t cannot be we'll just write it this way, the cube root of 1/2. All right, so the overall domain we would say here is from negative infinity to the cube root of 1/2 union with the cube root of 1/2 all the way up to infinity. That would work for the domain of g. So I'm going to separate these a little bit so we don't mix work up. All right, last one, the domain of h. h of t is equal to t sine of t, sine of 1 over t, sorry. Now, we have a product here, and the t part is fine. T can be anything. Sine is always defined. However, its angle in here is 1 over t, and that's not good. We can't have t in the denominator here. So we can have t in the denominator. We can't have t equal to 0 in the denominator. So t cannot equal 0. And that means that our domain for this piece would be from minus infinity up to 0, union with 0 up to infinity. Okay, so those are our three pieces. This is like our side work here, and our final answer is the domain of R, if we were to name this R of t. So the domain of R needs to be the domain of F intersected with the domain of G intersected with the domain of H. And it looks like, the first piece is giving us the entire real number line, right? But the second piece is saying, no, not the cube root of 1/2. And the third piece is saying, no, not 0. So basically we have the whole real number line, but no 0 and no cube root of 1/2. And so what that's going to be is we're going to go from negative infinity up to 0, union, pick up again at 0 and go to the cube root of 1/2, union, start up again at the cube root of 1/2, and go to positive infinity. And that is our overall domain for the vector. All right, so you'll have a few homework problems where you're working with limits and domains, not very different from what we covered in college algebra and calculus 1. The only difference is you've got to do it for 3 pieces. So pay attention to that part very carefully. Now the next topic is space curves. This is kind of why we need vector functions, because as we saw in 12.6, when we are looking at cylinders and quadric surfaces, when we have x, y, and z involved in an equation, it's giving us a surface, not a curve. The only way to get a curve in 3D space is with a vector. The problem is that a curve is a 2-dimensional object, and we want to look at it in a 3-dimensional space. And so multivariable functions don't work to give us curves. They give us surfaces, which are going to be 3D. So that's kind of the behind the scenes of why we need to do this. Now, our vector functions are going to, whoops, I did not mean to cross that out. We're going to use vector functions with one parameter in order to draw curves in space. Now, you just looked at, when we were taking the domain and the limit, the vector function right there, that is a vector function in one parameter. T is the parameter. Okay, so we always choose T. Every now and then you'll see a problem where you have 2 vector functions, so one of them is in terms of S. S and T are typically used. We do not use X, Y, and Z because those are the values of the coordinate, or the tripled ordered pair, our ordered triplet in 3 space. Okay, so what a vector function does, I've got a picture here that kind of demonstrates it, is a vector function is, it's just got these components, F, G, and H. And if you plug in a t value, like t equals 0 or t equals 1, you're going to get an x, y, and z value. It'll be a point. And so the vector function points at all the different points along a space curve. I'm only drawing like 5 of these, but imagine an infinite number of them tracing out this whole curve here. There are arrows on here that I can see, and so they're telling me the direction in which these points are kind of getting shot out by R of t. So it looks like they're starting on the left and then moving towards the right, doing a loop, and then continuing on towards the right. Okay, so the vector function allows us to get the points on a curve in space. We can't possibly graph those one by one. It would be really, really hard. In 2D, some functions were harder than others, but for the most part, we could create a table of values and we could graph a function. In 3D, that's not going to happen. we have to kind of work a little harder for it. Maybe not harder, maybe just more differently. Okay. So down below here, I've got this vector function. R of t is equal to cosine, sine, and t. Those are the x, y, and z components of this vector function. And this curve right here in blue, this is tracing out the vector function. So it's a coil, almost looks like a slinky, kind of stretched out. And let's see, if t was 0, we would get the point 1, 0, 0. That is a starting right there on the x-axis, right where they're showing. And then as t increases, it looks like the vector function gives us points that are higher and higher up. And this will just continue. It won't stop. It'll just continue like this. On the right-hand side, what we see is a 3D surface enclosed by the curve. So the 3D surface in there is not the curve. It's like as you're, this particular vector function is carving out its curve, it just so happens that a circular cylinder could fall inside of there. So that curve is just wrapping itself around in a cylindrical fashion. Now, if we were to look at the vector curve itself, and remember that these are x components, that's a y component, and that's a z component. If I was to take x squared plus y squared, that's going to be cosine squared of t plus sine squared of t. And we know from the Pythagorean theorem and right angle trigonometry, this is going to be equal to 1. So it turns out actually that x squared plus y squared is equal to 1. That would be the relationship that we could find within our x, y, z coordinates. Okay, so z itself is not part of this equation, but the equation x squared plus y squared equals 1 is a circular cylinder that opens up and it runs parallel to the z-axis. Okay, so there's a few things that we're going to be looking at. We're going to be looking at vector functions as curves, but we're also going to be looking at what the curve is wrapping around. What is the surface that can be described by the relationship of the components of our vector function? Okay, let's see where we want to go now. Okay, so let's look at this one. This is a hard one. I chose to do a hard one in here, and hopefully the ones that you have in homework are a little bit easier. In this example, we are asked to sketch the graph of a curve, and it's r of t equals a vector with components sine of t, cosine of t, and 1 plus sine of 8t. And t is going to run from 0 to 2 pi. All right, so let's see. I'm noticing in here that x and y have this sine and cosine relationship. And so, we just saw this up above. If we were to look at x squared plus y squared, that's going to be sine squared plus cosine squared, which is 1. And so that's what we're going to see if, the relationship between x and y is a circle. So on the xy plane, we're seeing a circle projection onto the xy plane. Okay. Now the z equals 1 plus sine of 8t. Well, that's just going to be a sinusoidal wave. So is a sinusoidal wave. Shifted up 1 unit. I know that because of the plus 1 that's in there. So sine of 8t, we can think about what would that give us. When t is 0, z is going to equal 1 plus sine of 0, which is just going to be 1. When t is, let's say, 1/2, z is going to equal 1 plus sine of, that'll be 8 over 2. Oh, sorry, I should say pi halves. When sine is pi halves, or t is pi halves, when I plug that in, I'm going to get 4 pi, which is still going to be 1. I better pick some better values here. Let's see, if we were to get, what would be good? I want there to be some other values. We could do pi fourths. No, that still wouldn't work. Let's just keep on going. We'll have t is equal to, let's see, if we did pi sixths, z is equal to 1 plus sine of 8 pi over 6 will be 4 pi over 3. Okay, well that's kind of helpful, a little bit better. So 4 pi over 3, start over here, 1 pi over 3 is about right there. 2 pi over 3 is about right there. 3 pi over 3 is about right there. And 4 pi over 3 is down here, okay, where everything is negative. So sine of 4 pi over 3, that is the y value is bigger. We're going to get negative root 3 over 2. So this is 1 minus root 3 over 2. Yeah, so this is starting to give us some of the values. That's kind of hard, right? We're going to like plug in all these t values going on here. You don't want to do this, okay? So the only reason I did this was to demonstrate how tedious this is and how to convince you not to do it. Let's just think of a sinusoidal wave. In reality, you would never graph these by hand. You would, in WebAssign, you may have like multiple choice, or in real life, you would use software to do it. So what I'm going to do is I'm going to take my sinusoidal wave and I'm going to wrap it around my z axis, because z is equal to 1 plus sine of 8t. So I've got a sinusoidal curve that projects down to the xy plane as a circle. Let's see how to make that happen. So, all right, this one's kind of hard for me. So we get something like that. And then I put my XYZ octant on there. That's about as good as I can do. It's like a bracelet. That's what it always makes me think of. It's like a bracelet that is very curvy. You could take a wire to make this shape too. But that's as good as I can get. So just to kind of reinforce some of this, the x and y components of our vector told me that there was a circular relationship going on. It didn't tell me to draw circles. It just told me that there's a circular relationship going on. And what that basically tells me is that when I get to drawing my z stuff, whatever it is, whatever that function is, I have to draw it in a circular manner. And so I drew my sinusoidal wave in a circular manner. Okay? So I want to just go back and X this out, and say this is too much work. Okay? All right. So that's one example of graphing a curve. Look for the sines and cosines, those sorts of relationships, to see where you have circular patterns going on. The next topic is the intersection of two surfaces. So in this particular picture here, this is called the Viviani curve. And what it is a regular old sphere that has a cylinder cutting through it, but not in the center. So it's not like the core of an apple that's being taken out by an apple corer. It's like the core off to the side. So it's just getting like a weird shape. Now notice that there is a curve of intersection that is created where the cylinder cuts through the sphere. And so we can actually find those things if we have two surfaces and we're trying to figure out like what's the curve of intersection. We can totally find that. All right. So let's do that. All right. In this first one, we've got z is equal to x cubed and y is equal to x cubed plus z squared plus 2. This is not totally obvious. I know it's not obvious. So let's kind of slowly walk through this. When I've worked through this problem, I found two different ways to parametrize it. But there are two bits of information I want you to know. First, try to get all variables in terms of t. That's our goal. The second thing is that as you do that, never, ever, ever take square roots to do so. Your answer will be accepted by WebAssign, but it will technically be incorrect. So the problem with taking square roots to do so is that when you take a square root, you should have a positive and a negative solution. So for example, I just, kind of an aside, if I had x squared plus y squared is equal to 7, and I isolated and I said, oh, y squared is equal to 7 minus x squared, so y is plus or minus the square root of 7 minus x squared. Each of those, the positive and the negative, gives half of a circle, not a full circle. So if you're trying to parametrize a circle, you cannot use one or the other of those solutions. And if you try to use both, then you have two functions in one component, and that doesn't work either. So don't do this, okay? This is not allowed. This is a no-no, okay? Can't stress it enough. All right, here's what we can do for this problem, which wouldn't require any square roots anyway. I'm looking at this and I'm seeing that z is equal to x cubed and y is equal to x cubed plus z squared plus 2. Now, when I see z is equal to x cubed, this is an explicit function. Z equals something, okay? So I'm thinking it might be good to let x equal t, because then z is equal to t cubed. And so now I have x and z in terms of t. Next thing I need to do is get y in terms of t. So let's see how we do that. And y will equal x cubed. Well, x is t, so I can go ahead and put t cubed there, plus z squared. Well, again, z is already something. It's t cubed. And so then we'll square that. And then plus 2, which boils down to t cubed plus t to the, if we have a power raised to a power, we multiply. So t to the 6th plus 2. All right, that gets everything in terms of t. So our vector function is equal to a vector with components t. The y component is t cubed plus t to the 6th plus 2. And the z component is t cubed. And that's it. That's all we do for that one. Let's look at another one, because they don't all work out like that. In this next one, z is equal to x plus y squared, which is an explicit equation. But then z is also equal to 2x plus y. So we've got z being equal to two different things. Well, all that means is that those two different things must be equal. So that's where I start. This implies that x plus y squared is equal to 2x plus y. If I move all the x's to the right and the y's to the left, I get y squared minus y is equal to x. Or I could rewrite that as x equals y squared minus y. Okay, well, that is an explicit equation of x in terms of y. So maybe I could let y equal t, then x is equal to t squared minus t. And then I should be able to choose either of the representations of z. And z, I'll just choose the first one, is equal to x, well, x is t squared minus t, plus y squared, which is plus t squared, and this simplifies down to 2t squared minus t. We would get the exact same thing if we had used the second z. All right, we have our three components. So r of t is equal to a vector with components. Our x component is t squared minus t. Our y component is t. And our z component is 2t squared minus t. And that's it. That's all we've got. All right, so the next thing to do is another problem. So let's see how this one works out. And here we have y squared plus z squared is equal to 9, and we have x is equal to 5y. This is one of those problems where you might be tempted to take a square root. Please do not. So I look first for, whenever I'm doing this, I'm always looking for circles, because whenever there's a circle as one of my equations, that means I should use the cosines and the sines, okay? So I have y squared plus z squared equals 9. I'm going to let y equal cosine of t. Oh wait, can it be cosine, or does it need to be more than that? I think it needs to be more than that because of that 9 that's hanging out there. So I have to think about what number, when I square it, gives me 9, and that would be a 3. So y should be 3 cosine of t, and z should be 3 sine of t. And then we just check it, right? Can always check. So y squared plus z squared is equal to 9 cosine squared of t plus 9 sine squared of t, which is equal to 9. Okay, that's good. So we have y and z in terms of t. Now we just need x in terms of t. So notice x is equal to 5y. Well, that means x is equal to 5 times whatever y is, and y is 3 cosine of t. So x is 15 cosine of t. And now we have our pieces. R of t is going to equal the vector with components 3 cosine of, whoops, that's not right. My x component is 15 cosine of t. My y component is 3 cosine of t. And my z component is 3 sine of t. And that's it. We're done. Okay. So those are just a few examples of how to handle a situation where you've got two surfaces intersecting each other and you want to come up with the curve of intersection. This next problem is asking where a vector curve intersects a surface. And unfortunately, the way things are spaced in here, the equation is on two lines, but it's x squared plus y squared plus z squared equals 5. And that's a sphere. So we want to know where they intersect. And you know, this is one of those problems where if you don't know, it's impossible, but if you do know, it's actually not that bad. What we have to remember is that the vector has x, y, and z components. What that means is that x is equal to sine of t, y is equal to cosine of t, and z is equal to t. Okay, we're going to take all of these and we're going to substitute these into the sphere to find the t value, or values of intersection. Okay, once we find the t values, we'll be able to find our x, y, z values and have the points. Okay, so let's try that. If I substitute these x, y's, and z's, then x squared plus y squared plus z squared becomes sine squared of t plus cosine squared of t plus t squared, and that's all supposed to equal 5. All right, well, sine squared plus cosine squared is 1. So 1 plus t squared is 5. T squared is 4. So t is plus or minus 2. Okay, so the points of intersection then we plug these into the parametric equations. So what we get is x is equal, I'm going to do the positive one first, so x is equal to sine of 2, y is equal to cosine of 2, and z is equal to 2. That's one point. The other point is at x is equal to sine of minus 2, y is equal to cosine of minus 2, and z is equal to minus 2. So we have two ordered triplets. I have not written them in ordered triplet pair. I've just written the parametric values for x, y, and z, but that's how we get it, right? So you substitute the vector curve components into the surface. Once you find t values, then you substitute them back into the curve to get you your points, okay? All right, I've got some fun examples to work through here. So this example is really straight from your homework. They give you a bunch of pictures of curves in space, and then they give you a bunch of parametric equations, and they ask you which one goes with which. And so we have to figure that out. I'm looking at these first to kind of see like if there's anything that stands out. One of them, this looks like a cylinder, right? This one right here kind of looks like a cone. This one right here looks sinusoidal. I'm not too sure about this one, 6. That's a little weird. Like starts off almost like a potato chip and then flattens out at the bottom. Not certain how to name that, but that's okay. I won't name all of them. I just want to name the ones that are like stand out as like, I know what that shape is right there. Okay, here's what we do. In part A, we are given parametric equations. X is equal to t cosine of t, y is t, z is t sine of t, and t must be greater than or equal to 0. Okay, if I was to take, it looks like I've got some sines and cosines in here, so I want to use my Pythagorean theorem in order to help me. So if I look at x squared plus z squared, that's going to give me t squared cosine squared of t plus t squared sine squared of t, which is equal to t squared. But notice this, y is equal to t. So t squared is equal to y squared. So I put that together and write y squared equals x squared plus z squared. Now what we learned in 12.6 is that this is the equation of a cone. But y equals t, and t must be greater than or equal to 0, which means y must be greater than or equal to 0. And I'm just getting that from the parametric equation and then the domain that they put on. So I need a cone, and it looks like it should open along the y-axis. And because y is only positive, we get 1/2 of a cone. It looks like number 2. Okay, so that's the match there. That's all we're doing here. Okay, let's see the next one. In the next one, we have x is equal to cosine of t, y is equal to sine of t, and z is equal to 1 over 1 plus t squared. That's an interesting one. All right, I see sines and cosines, so again, I'm going to take advantage of that and say, okay, well, if I have that, then x squared plus y squared is equal to cosine squared of t plus sine squared of t. That's equal to 1. Okay, so I have a circle relationship going on here on the xy plane. Now, if I stop right now and I go back up to my pictures, I'm looking for circular relationships on the xy plane. Look at 4 and 5. 4 is the cylinder. That almost looks like the one we want. 5 is cylindrical, kind of, except for that weird top that it has. Let's see which one we should choose. Z is going to tell us. Z is equal to 1 over 1 plus t squared. Now, Z, let's see, as t goes to infinity, what's going to happen is the denominator of Z is going to blow up, right? And so that means that the overall Z values are going to go to 0. And as t approaches 0, Z, well, if t is going to 0, then Z is just going to be 1 over 1, which is 1. Okay, let's see if that gives us any information. So if t gets bigger, Z gets smaller. And if t goes to 0, Z is going to 1. Okay, so that means at the start, when t is equal to 0, Z is equal to 1. Now let's go back up. I'm thinking this potato chip looking thing is where we need to go. I'm thinking that that's the start of it. And then as t gets bigger, we're going to, whoops, I didn't mean to select that. We're going to be going around in circles and spiraling down in a circular manner all the way down to 0. So I think 6 is going to be the one for us here. So I'm not actually graphing these, right? I'm just talking about the relationships and seeing if I can glean anything at all from that. Let's look at the next one. It's a little bit different, but kind of similar. So in this one, x equals t, z equals t squared, and y is that same ugly fraction, 1 over 1 plus t squared. Okay, well, let's look at this. If x is t and z is t squared, that means z is equal to x squared. I can just take that x equals t and substitute it into the expression of z equals t squared. So z equals x squared is a parabola on the xz plane. It opens up, okay? And let's see what's happening with y. As t goes to infinity, y is going to 0. And as t, well, I guess when t equals 0, I guess I should change my language there. When t equals 0, y is equal to 1. Okay, so let's look for something parabolic, and then on xz, and then as t gets big, y is going to 0. Let's see what happens. I'm seeing this one. That looks parabolic. Yeah. When t equals 0, y is 1. We're starting up here. And then as t goes to 0, it's going down to, as t goes to infinity, y is going down to 0. So I think we've got our parabola there. And nothing else really looks like that. So I think we're safe that this is going to be 5. All right, last one, and then we're done. In this last one, x equals cosine squared of t, y equals sine squared of t, and z is equal to t. right away, I see that if I was to add x plus y, I would get cosine squared plus sine squared, which is 1. X plus y equals 1 is a plane. Okay, and let's see, if x is cosine squared and y is sine squared, then we also know that x is greater than or equal to 0 and y is greater than or equal to 0. And then z equals t means, well, z is like an angle. So as t increases, your angle is changing. Okay, let's see what ends up happening there. Let's go up and look. The only thing I'm seeing that might be planar is this interesting sinusoidal curve that looks like it's on a, it's flat. So let's just kind of go back to what our problem was. We have x plus y is equal to 1. That would be a plane. X and y are positive. This is in the first octant where x and y are positive. As t increases, the angles are continuing to increase. So z is equal to t, and we're getting a sinusoidal shape. That's from the cosines and the sines. I think that's going to be our 1. I don't think it can be the first one that looks like a hyperbola, and I don't think it can be a cylinder, so we're stuck with 3. That's our last one. All right. So you see, it's not like a perfect science. There is a bit of a, not a guess, I'd say it's more of an educated guess, like looking at relationships and seeing how they kind of tie together with the picture that you're given. All right, if you have any questions on homework, please do reach out. I'm here to help.